Good afternoon, everyone. Welcome to the second Mildred Dresselhaus lecture. As you may remember, this lectureship was established last year in recognition of Professor Mildred Dresselhaus's outstanding scientific contributions and her inspirational mentorship and leadership. We get together for this lecture to remember Millie and to also celebrate accomplishments of distinguished scientists and engineers whose contributions resonate with Millie's lasting legacy and her lasting impact. The recipient of this lectureship is selected by a committee of MIT faculty from a list of distinguished candidates who are broadly nominated every year. And it is our great pleasure this year to be able to recognize and celebrate Professor Evelyn, who from Harvard University, as this year's Mildred Dresselhaus lecturer, and we're looking forward to hearing from her about her outstanding research. To open the session, I'm going to ask Professor Mildred, the Cecil Green Professor of Electrical Engineering and Computer Science, to deliver some opening remarks. After that, Professor Vladimir Bulovich, Director of MIT.nano and the Fariborz Massey Professor of Emerging Technologies, will be introducing our speaker and moderating the session. Once Professor Hu's lecture ends, we're going to have a Q&A session. And during that time, you can ask your questions either by typing your question through the Q&A feature of this webinar, or you can raise your hand and directly ask your question, and we'll be moderating that. So with that, let me invite Professor Mildred for her opening remarks. Muriel, I'll pass it over to you.
It's really a great honor to be giving a few remarks to open this, and thank you very much to the organizers for inviting me. Of course, Millie was somebody who was so wonderful and inspiring to everyone, both personally and professionally. I particularly want to speak today as chair of the Mildred Dresselhaus Medal that IEEE has recently instigated. That was probably my proudest achievement of my time as chair of all IEEE medals. And I definitely want to encourage everyone to consider nominating worthy candidates for this medal. It's a medal whose remit from the point of view of topics is very wide. We're really looking for people who have had an impact that goes beyond the technical, but that includes, of course, the technical achievements. But from the point of view of topic and particularly specialization, actually, we're quite wide. So please do consider nominating a worthy colleague, somebody whom you feel reflects well the kind of qualities that made Millie so remarkable. And with that, Vladimir, I'll give the floor to you.
It is truly an honor to recognize today's speaker, the Mildred Dresselhaus lecturer, Professor Evelyn Hu. Professor Hu is a Tarr-Coyne Professor of Applied Physics and Electrical Engineering at John Paulson School of Engineering and Applied Science at Harvard. She's presently a co-director of the Harvard's Quantum Initiative. Hu is a member of the National Academy of Sciences, the National Academy of Engineering, the American Academy of Arts and Sciences, and the Academia Sinica of Taiwan. She's a recipient of the NSF Distinguished Teaching Fellow Award and AAAS Lifetime Mentor Award, the 2019 SES Erringen Medal, and the 2020 IEEE Grove Award. She holds honorary doctorates from ETH Zurich, the University of Glasgow, Heriot-Watt University, Hong Kong University of Science and Technology, and the University of Notre Dame. And I am absolutely delighted to ask her to take over and tell us her story of transforming defects into opportunities by leveraging the nanoscale.
It gives me such great pleasure to try and express my gratefulness to Millie for all the guidance and mentorship she's given to me from the time I was a graduate student, and to be able to publicly express my gratitude for her and the inspiration that she's given to us all. Let me, as I begin, share a secret with you all, perhaps. A secret that, a common experience that I've had with Millie, and that somehow has seemed like a good luck talisman to me, a la Harry Potter. Millie and I went to the same high school, and you can see that Millie has talked about how Hunter High School was a real turning point for her. This, what you see on your screens, is a report from the Hunter College High School alumni update recognizing Millie's reception of the Kavli Prize. And similarly for me, Hunter High School was a turning point. I, like Millie, grew up in the Bronx. There are many divergences in our pathway, but I also appreciate the ability of an exceptional school and an exceptional education in being able to introduce young people to the world and giving them a wider perspective. Millie also commented very often in the beginning, the encouragement came from women. I think she was recognizing the influence of various important people like Rosalind Yallow. And I wanted to note that Hunter High School, when Millie and I went, was an all-girls school. And that was very important to my coming of age and the paths I took. And certainly the encouragement came from women such as Hunter High School, such as Millie, who actually provided guidance for us all. As you know, Millie is very often touted as the Queen of Carbon, and Queen of Carbon and so much more. And I show here a schematic of a single-walled carbon nanotube, something that Millie did much to lay the foundations for. And many of you know that this single-walled carbon nanotube seems to be a model of perfection, symmetry, periodicity, the kind of material many of us like to work with because of its beautiful symmetry, its regularity, and because in many ways it's easier to do the computations and analysis for such a material. So the question is, in an imperfect world, is perfection, is this kind of regularity, is this kind of symmetry a necessary precursor for transformative advances in science and engineering? And of course, my answer in this imperfect world is undoubtedly, there must be more creative ways to approach the wealth of materials and phenomena we have in the world. And it was Millie, in fact, who in her lifelong career recognized that there are unique opportunities at the nanoscale. At the nanoscale, you are able to transform the materials that nature gives you, what nature gives you by ways of electron energy levels, phonons, and a variety of processes. And you can engineer, you have a chance to engineer or re-engineer those properties through a strategic understanding of what you can do at the nanoscale. And with this kind of inspiration, in fact, Millie in the 1990s, beginning in the 1990s and continuing with work that's being carried on today rethought thermoelectric materials, materials that can control the exchange of thermal and electric energy for a variety of very important applications where we can harness electronic energy from heat or consequently use thermal energy to provide electronic information. So what I show here is an equation. Many of you may know this, and for those of you who don't be alarmed. The most important thing here is to understand that there is something called a thermoelectric figure of merit. And if you've seen this before, that figure of merit has quite a simple relationship to some fundamental parameters: the electrical conductivity, the temperature, the thermal conductivity, and something called the Seebeck coefficient, representing thermal power. The issue here is that when we seek to improve the electric figure of merit, that is to get a better performance or better exchange of thermal and electric energy, with the materials that nature has given us, even three-dimensional perfect crystalline materials, all of these parameters are interrelated. So that if you sought to increase the figure of merit by increasing the electrical conductivity, you would soon find that in most materials, thermal conductivity would follow in response. And so that limits the amount of optimization that you're able to achieve with the materials that nature has given. But Millie was very early to realize that there may be new approaches and new directions in engineering thermoelectric materials at the nanoscale. And this is an example, although her work began with some seminal papers in the 1990s, this is some more recent work that appeared in Advanced Materials and with Gan Chung, who is a co-author and I believe still works in this arena. And here are the insights that Millie realized, that if you can actually create a heterogeneous material, engineer a material that nature didn't give you, but take nanoscale components with unique properties of their own. For example, this diagram that appears in this paper shows layers of quantum dot structures that have altered electronic densities of states. They're embedded within a series of layers that have barriers or interfaces that are used to filter out and control electron energy levels. So quite simply, the heart of her idea was this: to use unique properties at the nanoscale that involve quantum confinement to profoundly change what we call electron density of states, and what I call controlled discontinuities, AKA interfaces. Now, why do I say controlled discontinuities? These interfaces, these superlattices, are intrinsic to the idea that Millie proposed, and yet very often interfaces represent a discontinuity between different phases of materials. They're often problematic because interfaces are sources of scattering and therefore decoherence for electronic states, photonic states, or phononic states. But used in the right way, they can all be brought together at the nanoscale to produce a material with far better properties than nature has given us. And so I want to take Millie's inspiration and tell you today a little bit about how we followed in my group those new directions in understanding and engineering materials at the nanoscale. In our case in particular, finding directions to engineer materials with a combination of photonic correlated with spin coherence, in those materials. And I want to give my thanks to the variety of the researchers in my lab who have graduated, who are currently working very diligently on this general set of issues, and members, including members of my lab who recently joined. Roderick Defoe is in particular a member of Tim Kasiris's lab, and we've had collaborations with Tim's lab, as well as the groups of David Ausschlam at the University of Chicago and Jörg Rottrup at Stuttgart. And by the way, Diana is currently a postdoc working at MIT. So how do we realize opportunities at the nanoscale, perhaps in a way analogous to the insights that Millie showed in working with thermoelectric materials? Well, we're going to take some unique properties at the nanoscale. We're going to take the building blocks of quantum coherence, but we're also going to work with defective materials, seeming imperfections in a material. So if we take a look here, this is part of a crystalline structure of something that's called 4H for a particular polytype of silicon carbide, and you see silicon and carbon here. What you see largely is a periodic crystalline structure. So that's the starting point. We begin with a perfect single crystal semiconductor material. But now what we're going to do is disrupt that perfection. We're going to remove silicon atoms from that material. So we create what I call silicon vacancies here and here. And having insulted the material in this way, we're now going to look for opportunities. So this picture that I've given you of our starting material, vacancies in silicon carbide, perhaps is the wrong way to look at the problem. The way I've presented this to you is that we're taking a perfect material and we're making it somehow less perfect. But if we were to take the half full rather than the half empty view of science, think of those vacancies not as something missing from the material. Think of those vacancies surrounded by the electrons in the local atomic vicinity as atom-like entities with particular electronic and spin states that in turn are embedded within a complex wide bandgap environment that in fact has used tremendous sophistication to actually electrically isolate these atom-like entities. So with this point of view in mind, let's ask what indeed are the electronic, photonic, and spin properties of the defect? Well, a very simple and summary way of regarding it is to look at this simple electronic structure to the right. And to note that the silicon vacancy, which is not a vacancy, but an actual atomic entity, has ground and excited electronic states, as you see represented here. And those, by exciting electrons from ground state to excited state, one pathway to releasing that energy may be in the emission of photons with a distinctive energy. The silicon vacancy also has an electron spin, and it's known in this case that the electron spin is 3/2. And therefore you see that these electronic states, the sublevels, depend on the spin, the particular spin, or the projection of spin. Very interestingly, but very importantly in this electronic structure, there is this titled MS, which means it's a metastable state. I call it a shelving state. It's a state that actually helps to purify the spin state of the vacancy as we continuously cycle it through a series of excitations and release of energy. What you can see here is that the various excited spin states, 3/2, 1/2, have different probabilities or different rates of interaction with this metastable state. And therefore, what happens is that the various spin states, as they de-excite, are held for more or less time by this metastable state. And this, quite simply and superficially, unfortunately, is the basis for a way that as we excite and de-excite, we continuously cycle through this process, we can actually purify the spin state that we see observed from the silicon vacancy. So the end result of all this and the takeaways are this seeming absence of silicon actually has quite a character of its own. It has the properties that its unique photon and spin states are correlated and coupled. We have, therefore, the capability of, by using optical signals, we are able to prepare and read out spin states. And more profoundly, in terms of the wide range of applications we might be able to realize, think of it this way, that we have an atomic scale reporter with a quantum mechanical property called spin, which is exquisitely sensitive to the magnetic or spin atomic environment. And we have associated with that spin reporter a unique photon energy that can take this information and propagate it over long distances far away from the very local information that this silicon vacancy can give us about its environment. But having said that, let me say, but wait, this is but hold on. And this is the first of two but waits that I'm going to introduce to you. The but wait is, I've told you about an atomic scale entity with a combined correlated photon and spin information with exquisite sensitivity to its local environment. But as indicated symbolically here, how can we possibly attain enough signal from a single atomic scale defect that's buried someplace in a block of material? And indeed, if I try to excite a block of material and take a look at the resulting photoluminescence spectrum that this emits, at room temperature, what I get is an almost featureless spectrum that basically tells me very little to nothing about the local environment. If I cool my sample to 77 Kelvin liquid nitrogen temperatures, I begin to see some characteristics, some identifying indication that there is indeed a silicon vacancy within. But what you can see is that the peaks are faint and they're basically almost lost within the background. And notice here that I have two peaks identified. One is called V1, one is called V2. These are in fact the different signatures from the slightly different silicon vacancies. I showed you two vacancies in earlier schematics. There are slight differences in the crystallographic environment that lead to this distinguishing difference in the photon emission signature of the silicon vacancy. So this is both good and bad. It's very impressive that a missing silicon, has such sensitivity to its home location in the starting crystal that it gives you a distinctive photon signature. But the what if remains. And the what if is, how are we ever going to pull a reasonable signal out of the noise of these spectra? So the answer also lies by our ability, our insights, and our talent to manipulate the nanoscale. And the way that we're going to proceed is to create an integrated nanoscale environment for our silicon vacancies. And I've introduced that concept symbolically here. These parentheses indicate an isolated environment that induces a conversation or a coupling between our silicon vacancy, the atomic unit of interest, and the environment. So think of this as a breakout room at the quantum level, where we place our atomic scale silicon vacancy into an intimate and isolated conversation with its environment, and its environment actually happens to be a discrete level of optical or photonic states. So in effect, what I want from this unique environment is to create a precise and distinctive amplification of the signal from the silicon vacancy. It's a precision response that has to take into account the frequency, that is the photon energy or frequency that's emitted by the silicon vacancy, therefore a reflection of the precision of the electronic states of the silicon vacancy. But it also has to identify and target precisely the spatial location of the silicon vacancy. And remember, we're talking about atomic scale entities. So this precision response to frequency and spatial location is a way of uniquely coupling to this silicon vacancy by this environment. And in addition, I hope it goes without saying that since we're talking about photons, since we're talking about amplifying photons, and we're talking about the unique photons that are emitted from the silicon vacancy, this environment has to be very low optical loss. This environment, and far lower than many of the cavities you think you know, those in the audience who worked with cavities, and I've already given it away because this is what I call this environment. I called it a cavity. This cavity has to have the capability to recycle, in essence, store that photon energy as it goes back and forth between the emitter and this environment until I ask that information to be released for whatever purpose I wish. So that is the wish list, what I want of this kind of environment. What does it actually look like? Well, it actually probably looks much more humble than you might imagine. It is basically, this is silicon carbide. This is basically a suspended, one-dimensional, modulated structure. You can see that there is this marker here that states 1 micron. There are holes that are punched into the silicon carbide, and that's what I mean by modulated. I modulate the structure by a series of periodic holes. These holes, center to center, are about 100 nanometers in distance. This, it may be difficult to see, but this one-dimensional like structure bridges. It's a suspension bridge that is elevated over the substrate, And it needs to be elevated because I want to minimize optical loss from this bridge to any other source. Now, we call this bridge a photonic crystal with engineered photon states. Some of the best, most seminal work on photonic crystal structures has come from MIT. And the term photonic crystal is in acknowledgement of the fact that a regular crystal, for those of us who work with semiconductors, for example, a regular periodic crystal has well-known states and bands of energies for electrons. This is the analog with well-defined states for photons. But basically, the message I want you to take away is, humble though this may appear, this is in fact, and you'll have to believe me, and I'll show you some evidence, a precision, finely tunable instrument with an exquisitely pure response that will make the silicon vacancy within it sing. Now, to show you a little bit more detail in terms of how it sings and what effect this nanobridge has, I show you an electromagnetic simulation of what happens if I were to launch light through this nanobridge. In essence, what happens is, for the right frequency of light, there are standing wave patterns that are set up. Those standing wave patterns happen with wavelengths that actually correspond to this kind of structure that I superimpose. That is, the standing wave patterns show you concentrations of very high electromagnetic field that are in these regions about 100 nanometers apart from each other. And what you see basically are that there are very high regions of electromagnetic field that are localized in volumes of about 100 nanometers cube. So very high field in a very small volume. Now, to give you some indication that this works, that we indeed can bring signal out of noise by building this very bespoke, that is particularly generated, uniquely distinctive environment that we design for the silicon vacancy within. If you remember the photoluminescence spectrum I showed you at the beginning, even at low temperature, we could hardly distinguish the signal from the silicon vacancy from the background noise. When we place the silicon vacancies within this cavity, and we don't do anything to fine-tune the response or the conversation between the cavity and the silicon vacancy, we see immediately, and this is at room temperature, this is untuned, this is the particular V2, you can see that the signal to noise is enormously better. There's an exquisitely thin, narrow response that corresponds to the silicon vacancy within this cavity. Now, you may think that what I've done with the cavity actually is taken a bandpass filter, perhaps. And with the bandpass filter that is located around a particular peak of interest, I've managed to just filter out all the surrounding noise. I want to emphasize that this cavity is much more profound in its effect than simply filtering the response. In fact, this cavity brokers a unique conversation between electronic and photonic states. And I know that this is a lot to, for those of you who are hearing this for the first time, it's perhaps a big, complicated concept to lay before you. And similarly for this equation, but let me just try and simplify this. This is an equation that actually describes how the cavity brokers that conversation. And if the only thing you look at is this part, Purcell factor F is the ratio of the emission rate, the photon emission rate of our silicon vacancy in free space, that is free space in bulk material, that is in the material as usual, if I didn't do any consideration at the nanoscale, and the emission rate in the cavity. This is the critical feature. And our hope is by instituting this unique environment that we can actually make this Purcell factor quite a bit larger than 1. And what that means is that somehow we're brokering a conversation, an exchange, an almost lossless exchange of energy between electronic states in the silicon vacancy and photon states in the cavity, so that the emission rate in the cavity is maybe orders of magnitude higher than it would be normally. These components tell us what is important in doing this. And it's a different way of describing what I said initially. This high Q over V, this is a quality factor. It describes the resonance of the cavity in frequency with the silicon vacancy. High Q over V means that I have a really high field, it's exquisitely in tune, and it's concentrated in a very small volume. This component is what I spoke about earlier in saying I need to pinpoint exactly where my silicon vacancy is, and be able to make sure that that field overlaps the position of that atomic scale entity. So in essence, this cavity is not simply a filter. This cavity engineers a change in the spontaneous emission rate of the silicon vacancy. And that is something that is profound. If we go from further to show the possibilities of this cavity, what I show you here is the cavity mode. So we're going to go the next step, and this is at a low temperature. This is not at room temperature. This is at 4 degrees Kelvin. And actually, what we see that when we can actually do better in picking out the unique signatures of the silicon vacancy, I told you about V1, V2. V1 actually has an excited state, which we call V1 prime. But the purpose of showing you this diagram is that we can take this beautiful instrument that we've made, humble though it appears, and we can change its resonant frequency actually by adsorbing condensates, gaseous condensate onto the cavity. So by doing so, we're changing the resonant response of our instrument. And as we do it, we change this cavity mode, the response, so we shift it to be in frequency resonance first with V1 prime and then V1. And what you can see as we do that in succession, we can get this enhancement, this Purcell enhancement of as high as 75 for one of these transitions. Now, this is almost 2 orders of magnitude. And I go back to the first what if that I asked you, because I'm going to, or what if hold on, because I'm going to go on to the second hold on. But to say that what we've done is actually address this issue of taking perhaps a single atomic entity and then getting enough signal. Now, of course, we don't really have, in what I've shown you, a single atomic entity. although we may have 5 or 10. And I'm going to go on to the next hold on, but I want to, as we move along our journey, actually talk about this idea of resonance and exquisite instrumentation and acknowledge Millie's exquisite capabilities as a musician, and the resonance and the pure tones that she was able to achieve in that other very talented manifestation of her life. So hold on to, because in this very short introduction to you, I've skipped over a lot. Hold on, there should be lots of questions you're asking. How can we controllably create the defects, a single vacancy, and ensure that they have the electronic, photonic, and spin properties that I've glibly told you about? How can we sculpt that nano environment that I showed you without giving you details? And yet, using the tools that a sculptor uses, how can we do that without creating further defects? And then, if I do create further defects, there must be other nearby defects in this environment. How is it, what is the effect of those other nearby defects? What are they? And how will those other nearby defects within that small volume, about 100 nanometers cube, how will they affect the ultimate performance of the silicon vacancy that I'm interested in? So just to show you and to say, this is partially as far as we're going to go on today's journey, but to let you know that new experiments are going on even as we speak. We are taking this nano cavity, and I show you this in this blow up. We've been recently doing experiments to see how can we change the silicon vacancy and its defect colleagues in this environment. How can we change it by coupling in additional energy, like laser irradiation at different frequencies, or thermal annealing? We've actually seen very interesting performance. We've seen the ability to improve the signal. We've seen the ability actually to make the signal go away, which may actually be exciting because it may be a harbinger of the fact that maybe we can have means of nudging the defect into the right spatial location. But the end result of what I want to tell you here is that we can also use this nanoscale cavity not only as an amplifier, but because it amplifies the signal, use it as what I call a nanoscope to reveal local atomic environments. And I say all this in deference to Millie because it was always Millie's interest to be led by the science, to go down those wonderful rabbit holes of inquiry and excitement, always taking the big picture, understanding the applications, but wanting to understand the detailed science as well. So at this point, I think this is an appropriate resting spot for the journey that I've tried to take you on, that was inspired by some of the insights and the approaches that Millie espoused throughout her career. She's given all of us guidance along our collective journeys, and wonderful recommendations to follow our interests, have the best available education and training, set our sights high, always be persistent, keep our options open, accept help when offered, and always be prepared to help. So with all the guidance that Millie has given, all the transformations that she's made personally in science and in the sociology of science, in opportunities that she's created for a vast community of people as scientists, as students at every phase of their career. I think Millie's legacy, of course, relates to her tremendous accomplishments, which are a lesson to us all. Her energy, which was boundless. And I just have a short story I want to tell here. Millie served as the chair of a visiting committee for a science and technology center that I was involved in while I was at UCSB. And I remember that day where the committee had met, they had come to some advice and recommendations. Millie was scheduled to leave from Santa Barbara to fly to Israel. And she was talking about how she would arrive in Israel, eat a short dinner. She was going to perform in a string quartet. And about a half a day later, she sent us her notes, the report that she had generated from the visiting committee. So her energy is something that we can all emulate, and many of us will fall short of. Her optimism was continuous and continues to inspire us. Her humility throughout all of this is singular and unusual. With all her accomplishments, I think it is an important lesson to her all. But I want to end with one comment that I've remarked on in terms of how, when we honor Millie, and if you look at the multitude of encomiums that have been given on her behalf, Millie is celebrated for all her legacy, but Millie is also described as being beloved, our beloved Millie. And I want you all to think, how often have we talked about a colleague, a role model, as being beloved? Maybe this is a gender-specific word, but I think not. We look to see accomplishments. We look to see where there are pioneers who venture boldly into new areas. But we don't often think about scientists, role models, engineers, our colleagues as being beloved. And in fact, that is an incredibly difficult characteristic to aspire to. But I think, you know, if you think about what beloved means, it means a degree of trust. It means a degree of willingness to follow, to believe, to listen to. And we all know, particularly with the lessons of the past 8 months, or maybe the past 4 years, that for a scientist and engineer to be beloved in that way and to have trust in that way makes the difference between, I think, effectiveness and the ability to affect change. So again, thank you all for being here to allow me to express my gratitude publicly to Millie. And thank you, Vladimir, Farnus, all of you for sharing, and MIT for sharing Millie with the world, and for sharing her legacy in so many aspects. Thank you.
Thank you, Evelyn. I'm going to clap, and I'm sure many, many people around the participants will do exactly the same. Indeed, it has been an inspiring lecture you have given us. And thank you very much for the echoes of Millie that you have indeed concluded your lecture with. There are many questions that has indeed arrived. Please keep sending them through the Q&A tab if you have additional ones. And you also are welcome to raise your hand, and we will do our very best to call you. So let me start by asking you a few questions. And I will choose in this case to read them, but sometimes I might actually call upon our colleagues to ask them themselves. From Nick Feng, question, Dear Evelyn, the example of Purcell enhancement on silicon vacancies is very exciting. What can we expect as the ultimate limit of such Purcell effect? And what are the limiting factors in this case?
That's an outstanding question, and it's one of those grand challenge questions. Nick, if you mean by what do you think of the limit in the perfection of the cavity in terms of the Purcell quality, or what we are able to achieve in what we call strong coupling? It's a wonderful question, and I want to say the following. For those of you who have even seen what I've tried to show here, obviously I showed you the cavity and you could identify, are there imperfections in the fabrication of the cavity itself? Is that the sculptor's tools fall short? Are there defects that we introduce by way of creating the structure? Or is there roughness? Is there imprecision in defining the measurements? There is all of that, and yet fundamentally, and we're not yet at the limit at what I showed you, ultimately, when we talk about Purcell enhancement and defects, when we talk about optical loss, we talk about anything that takes the energy that we put into that cavity and absconds it for its own. And that includes the very structures themselves that we want to further study. And so, in a sense, what is the limit? And Nick, I'll sidestep that, but I would love to have a profound discussion with you at some time. But to say, this is the perfect tool for us to begin these explorations, particularly when we're looking at atomic scale defects, because the sensitivity to defects and the interrelationship with the performance of the cavity are so tightly intercoupled that we learn about one by, even if we give up on a parameter, by looking at the other.
Evelyn, continuing on that, indeed, the defects themselves are could be generated. The question from Dorsa Parvis is, can you comment on the scalability of defect engineering? Can we count on their collective ensemble anytime soon?
What a prescient question. And it's always an issue of scalability. I want to answer in two ways. And I have to say that with this issue of defects, and there is a sophisticated audience, I'm sure, that realizes that these are not the only examples of defects. There's something called the nitrogen vacancy in diamond that is actually the poster child and has had a long history. In terms of scalability, that is the, I don't know, $3 billion question, whatever, for all these quantum technologies. And I have to say the following, that there have been a variety of approaches that people have used by trying to use precision instruments to form the defects, by using precision masking through nanolithography techniques. But I also want to say that in many ways, the formation, even with all that precision instrumentation, is nevertheless stochastic. And that's why I believe what we understand from the fine tuning, if indeed we can use the cavities themselves and introduce a post-processing step, if we understand that enough, even though that may not be scalable, I don't know if we go back and introduce a fine tuning to each component. I think that we need the means to fine tune after the introduction of the defects. But like Millie, I'm an optimist. And that is the reason for science and engineering to proceed. And I believe that there are techniques that we're not yet aware of in nonlinear ways to fine tune, perhaps use the cavity itself to tune into to resonance.
If I can maybe add to that, since you mentioned that clearly beyond silicon vacancies, there are other types of vacancies we could also examine. I would also imagine that you can also come up with a doping process where you might use molecules as active spin states. Has that been significantly investigated, and what are the challenges as compared to using the crystalline semiconductors with their own vacancies?
That's a wonderful question, Vladimir. And the answer is yes, in certain ways. For example, there's work, to hesitate to, there's a variety of work going on that introduce, for example, rare earths into glass-like material. And I think that the field is waiting for innovation. Rare earths have certain capabilities because they carry their own natural sort of, they're the introverts of the atomic world, which means that they're relatively insensitive to the environment around them. But I think what you're suggesting, Vladimir, is that wonderful possibility at the nanoscale, where the original ideas that you have, that interfaces are bad, that heterogeneity is bad, I believe that there are ways to perhaps engineer around that. And there have been examples already that people are trying.
More straightforward question on, you mentioned during your talk that you're able to tune the cavity by nitrogen adsorption. The question is, can you explain exactly how that happens? Why does the cavity get detuned?
So basically, I think all of you know, basically it changes, if you want, changes the mass or effective index of the material. So particularly with a wind instrument, but with all instruments, you know that the tones that you get from your instrument depend very much on if it's wind or string, the veneer, the tuning, the thickness of the components. And so in a sense, take a wind instrument and you're adsorbing, you're changing, but you're doing this at the level of atomic layers. That's the difference in sensitivity. So you're fine tuning the response, and it goes back basically to the basic physics you do. You're changing the resonant response, but you're changing the resonant response at far higher frequencies than we're used to. And so monolayers of adsorbed material shift the resonant response of our cavities.
The Purcell effect, as you demonstrated it there, indeed you're able to achieve at room temperature. This significantly leads us to say, well, maybe quantum computing will achieve room temperature operation, if that is one day what we truly aim to do with this idea.
I think
is that feasible?
So I will say, is it feasible? I'm a school of people who believe that there is that possibility. It is because, so will it happen tomorrow? I don't think so, but the tantalizing prospect is, when I described the glass full, to look at the components within a structure as not being an absence, whether it's defects or you add a molecule, but it is within this wide bandgap semiconductor. And the wide bandgap semiconductor has its own band structures and where electrons are allowed to live. It doesn't buy the components absolute immunity, but it's a different way of thinking of creating your structure. Begin with the package, understand the electronic structure of the package, and all the manifestations, including strain and electrical changes and how you can change the package, and then embed your atoms or your vacancies within that package.
So another question that came up is mathematical modeling of the phenomena that you observe. In many ways, the coupling, the Purcell effect, those are well understood mathematically. Are there needs for additional mathematical models to describe properly what happens down on the nanoscale?
Absolutely, and many of you in the audience know that the seminal work, the seminal computational tools, and even today the more sophisticated tools are being done at MIT. Absolutely, more mathematical modeling. There, some of you in the audience may be aware of something which we now call, although it's been in existence for a while, inverse design or inverse modeling, which is to take rather than go and design forward, thinking you know exactly what you want and how to optimize it, take the factors that you really want to optimize out of a fairly complex system, focus on that, and then carry out the design process. And that is actually providing tremendous insights, because the geometrical designs that come out of it are completely not to be expected. And so the short answer, Vladimir, is absolutely yes. More modeling tools.
Wonderful, Evelyn. Evelyn, I know we can keep on asking you questions, but I want to, at this point, thank you one more time. I'm actually going to, repeat the words that Peter Fisher, the head of physics, just related in the Q&A, thanking you for using the word beloved as a way of describing Millie. Indeed, it is rare we find an individual that we are able to relate in that way. I think you epitomize many, many, many of those qualities, and we very much appreciate you in so many ways for echoing Millie by the lecture you have just given us. We have a small memento of this particular experience, so that as you look around your office one day, you're able to indeed remember this particular event. And I will go ahead and hide my own image so you can look at it more properly. Here we go. And tell you just a little bit about this particular object. This is a hand-blown glass pumpkin, creation of the artisans of the MIT Glass Lab, which sits adjacent to MIT.nano in the heart of campus, and it borders with its windows, just like MIT.nano, the improbability walk, which is a garden passageway that we named after Millie and her love for, walking, and her love for, recognition that her journey led her to MIT was a set of improbable experiences. Well, just as you had described in your own talk, the frequency and spatial location intertwining, the intertwining in this particular object is the intertwining of the Institute's maroon and gray colors with delicate precision. This sculpture embodies the glass blower's creativity and understanding of the fundamental properties of matter, a reminder of the insight that you have shared with us, and indeed Millie has indeed done throughout her life. MIT.nano and MIT community at large offer this unique memento of MIT creativity to you in sincere gratitude for the multitudes of your contributions to science and for this presentation, which I shared with us for the Dresselhaus lecture today. Thank you so much, Evelyn. Really appreciate it.
Thank you, Vladimir. It is I who should thank all of you. I shall treasure it, truly.
Well, with that, we will conclude the Dresselhaus lecture for year 2020. And thank you so much all for attending. Take care.
Thank you.